everyone. Good afternoon. Hope you're all doing well. Surviving midterm season. So I put up some details about the midterm, so you can check that out. I put the two previous years that I taught the course. I didn't teach it last year, so I decided not to post that one because it's not the same exact style as I use. So anyway, these are the last two that I taught. You can see an example of what I'll include. You'll see that they're multi-part questions, which maybe each part is much faster and less depth or complexity than the problems you did on the problem sets. So likely I'll do something similar for this year's midterm. Consider two problems. First one may have some short questions on it, just like these ones. So check those out. And I put all the aids you can have. In particular, you can have a page of whatever you want to write on it. So you can copy stuff from the book, whatever you want to put on there, two-sided. Chatting with students after previous year's exams, those who spent a lot of time preparing those, I asked them if they actually used it, and most say no, not really, because once they figure out what to put on there, then you kind of know that material. At any rate, it's a great exercise to do anyways, thinking of what kind of things you need, any equations you need or use. I don't want to test you on your memorization necessarily, but your understanding of the concepts. Any questions about midterm? Yeah. This year's midterm will not be different than the previous years necessarily. I mean, I'll rethink it from scratch, but those will be a good guide of the types of questions that I'll ask you. The coverage, I didn't even post the coverage. Anyways, the coverage it's up through, I included a little study sheet, I'll post it after today, of just the topics. Yeah, follow on.
Yeah, sorry. So if we were to study off previous midterms, would the content on those midterms be the same as what we expect on our midterms?
Would the content be the same? Yes. The content on these two is very similar. This year we are a little later, so I added acceleration. So that's one thing that's not on those problems, which is a good point that maybe I'll post additional acceleration polygon problem, so you can practice that as well. Otherwise, the content. I think there's one thing, mechanism inversions appear. I may have asked a question about mechanism inversions. I didn't really cover that this year. We kind of used it for instance center calculations, but we didn't cover it in detail, so don't worry about inversions unless you chatted with me about those. Yeah.
We need to use the faculty template
For the age sheet, I don't care what yours looks like, so you can use whatever. Yeah. If you're taking it with exam services, they may care, but I'll tell them that I don't care. So yeah.
Can we print, or do we have handwritten?
Say it again.
Can we print, or
You can print it or handwrite it, whatever you want. Yeah, the aid sheet. Yeah, you can put the whole textbook on it if you want. Then you won't be able to read it. Yeah.
Sorry, I missed that question. Laura said, do we have to put the age sheet on the
I'm not asking that you use the template. So whatever you want to use for the aid sheet is fine with me. Yeah.
Did we narrow the time duration for the answers? 45 minutes?
Oh, so I wrote 45 minutes here. We have an hour blocked off. So we're going to use the full time. So we're starting at 10, but we'll start as early as we can. And then the exact amount of time, it'll be at least 45 minutes. Maybe we'll have 50 minutes, depending on how quickly we can get started. Yeah. Yeah, I'll think more about the exact time so that anyone who's taking the exam with exam services will have the same time as we have in person. Yeah.
do we have to use pen for this exam?
Do you have to use pen? No, and I understand maybe if you're drafting, you want to use pencil and erase, but we're going to use CrowdMark. So I put a note here, don't write on the back. We're going to scan all your papers in a scanner, and then we'll grade them online so then you can access them easily. It needs to be visible. So If you have pencil that's too light and we can't see it, then we may miss things. So we just want it to be bold marks. If it's just some construction lines or something that's not that important, you don't need to worry about it so much. It is hard for us to scan whatever it is, 1,000 pages and have everything be readable if you use too light of a pencil. Any other questions about the midterm or anything else for the course? The practicals, I'm not going to have problems about math. I say that, I'll say on the study guide that I'll post today, the material on the practicals is also fair game. I'm not going to have MATLAB problems, but some of the concepts or what I'm trying to get you to do in the MATLAB practicals will be fair game, those concepts, maybe incorporated into other problems. But I'm not going to give you coding problems on the midterm. Okay, so today we're going to be basically finishing the formation of loops, drawing and finding vector descriptions of mechanisms. Okay, and these need to describe the motion of a mechanism. And next lecture, we're really going to get into solving complex loops. Today, we're going to solve a simple one. But just to remember, our vector loops, right? This is going to be a sequential set of vectors, one after the other, going around our mechanism. And they need to capture the motion. So that's going to be our main theme for today, is how do we design a loop which captures the motion of our mechanism? And we want our loops to be as simple as possible. But if we make them too simple, they're not going to capture the right elements. So we're going to talk about what that means today. And you'll remember from last time, we had two classes of variables. We had our independent variables. And independent means we can choose them. Independent, so that's like our inputs. Inputs, these are independent variables. Okay, and our outputs, or things that are unknown, maybe unknowns is a better term, because it's not just the output, but any variable that we don't know, those are going to depend on our inputs, and so those are our dependent variables. Okay, so we'll call them I, V, and dV. Okay, so those are independent and dependent variables. We're also going to have constants. So things that are not varying at all. And sometimes we may have some variables that depend on each other with some other expression. Like let's say you just know a relationship between two variables because of something in the mechanism. So there might be some that it's hard to classify in one of these. And we'll talk about some examples of those later on. Okay, independent variables, we can have these as inputs. And we said before that these should be equal to our mobility of our mechanism, right? Those are, a mechanism requires mobility, number of inputs to specify its motion. Okay, so if it doesn't equal the mobility, that means you have some problem. Either it's unsolvable if you have too many of them, or if your mobility was 0, for example, you wouldn't need to study anything. It's all fixed. So we wouldn't really need to do this whole process. So it should equal, and that means you have a nice problem that can be studied using this method. Dependent variables, we said we can have 2 that we can solve for. So we can solve for 2 of these per loop. So each loop that we generate, each of these sequential vector loops, will allow us to solve for 2 dependent variables per loop. Okay, so these are our basics. If you want to make a loop that gives you something useful, you need it to satisfy these 2 criteria and capture the motion. So that's what we're going to do today. And we're going to look at some examples. I'm going to give you 2 examples, one which is a good one which is a bad one. So we're going to start with a 5-bar mechanism. Last time we did a 4-bar. So I'll just do the same thing for a 5 bar. And you'll know, remember a 5 bar, well, I'll draw the whole thing out here. 5 bar is like a 4 bar, just with an additional link in it. Are you guys able to hear me okay? We have some noise. Is it okay? Yeah. Okay, great. So here's our links. It's very nice to number them before doing your vector addition, because it's handy to number your vectors the same as your links, which means like I'm going to put a vector here along link 2, and I'm going to call that R2. R3, R4. And you remember last time, you can choose whether to keep your vectors going the same direction, or if you want to, you can reverse them. It's equally valid. And you can just choose them whatever you want or whatever's handy. It only affects, we'll call this R1 at the bottom, the direction of those only affects how you write your loop equation now. Right? We formed a loop. We go all the way around. And so we can write our loop equation. And we'll come back to our vectors and everything, or our variables in a minute. But our loop equation, we just start at any point. You can choose a point at random. Maybe it makes sense to start at one of the base points in your mind, but ultimately it doesn't matter. We could start here, for example. I'm going to start at point B. And I'm choosing to go counterclockwise around the loop. So you can start anywhere and go either direction and write a loop equation. So I'm going to go counterclockwise to form my equation. So I'm going to start here. We're going backwards along R2. So that means we have negative R2. We're going forwards along R1. So that means plus R1. Forwards along R5 means plus R5. Backwards along R4 is minus. And we're not quite there. One more, minus R3. And we're back to the beginning where we started at point B, so it's set equal to 0. OK, let's say you wanted to start in a different point. Let's say you wanted to start up here at D and write your equation. You'd write the exact same thing. You just switch where these vectors are in the equation, right? You could start there and go counterclockwise, and you'd get the same equation. OK, if you went the other way, if you went clockwise, you would just put a negative sign in front of everything, right? All the directions would reverse. So this is the clockwise. I'm going to write a counterclockwise version. It's the same equation. Right, so either one's valid. So you can go around either way, and you can start anywhere, develop your loop equation. OK, and we'll remember there's actually 2 equations here. We're going to divide this in our next step, which we're not going to go to right now, but we will for another mechanism. This actually has a horizontal and a vertical components. Two equations are in each line of this equation. Was there a question? Yeah.
Yeah, sorry, could you just repeat why you chose R1 and R5 to be in that direction?
You choose your vector direction, whatever you want. So you ask why? Because I wanted it to be up instead of down, right? You just have to choose. So the endpoints should be pretty clear. For this mechanism, there's nothing else logical to do for where to put the endpoints, but the directions are up to you. It just changes the sign of one of those terms, and you would define a different angle. So this is my theta 5 based on how I did it. If you said you wanted to put it the opposite way, you'd get a different theta 5, because the angle would be up here all the way around. So it would be my theta 5 plus 180 degrees, and that would change the sign here, and we'd get the same equation. Yeah. OK, so this is our formation. Does it satisfy everything here? So we're going to ask ourselves, does it capture the motion of the mechanism? And yes, like every vector here has an angle, and each of those angles corresponds to one of my link angles. Right? So each one of these, we could put the angle in there. And if I told you 5 angles, right, that tells you everything. You'd be able to draw the mechanism, right? So this loop captures the motion of that mechanism. If you'd cut off part of the loop, like let's say we just did R2 plus 3 and then we skipped all the way down here. So we skipped links 4 and 5, and then we went back. Like that's a loop you could draw, but it totally skips out on 4 and 5, right? It doesn't capture the motion of D, and it wouldn't be able to predict what the mechanism's doing, because links 4 and 5 are important. They dictate what's happening in the mechanism. Okay, so you can't skip key points. But sometimes you will have choices. Like what if there was some extension here to point E? It's attached to link 5. But what if I didn't ask you anything about point E, and you didn't care about point E? Then you don't need to put a vector out there, right? So capturing the motion of the mechanism means capturing whatever you need to know about it. So point E is just kind of along for the ride here. You don't need to include it. If I ask you to find the velocity of point E, you would need to include it, right? You'd need to make a loop that goes out there somehow and then continues on. So you'd need to make a different loop to capture that part of the motion, okay? So some of the basic loop for a mechanism usually is kind of set for you. It has to capture all the basic elements. Some things may be optional points or whatnot. Okay, so this is a loop. Let's think about our independent and dependent variables now. So we'll ask ourselves, what's the mobility of this mechanism? What's our mobility? 4-bar mobility has of 1. 4-bar has 1. This has an additional link. We did it before. What's the mobility? Is it the same as a 4-bar? Everyone's doing it in their heads here. It's been weeks. I told you the answer in class. Anyways, everyone's calculating it. Any brave one on a? 2. 2, okay. We got it. That's good. 2. So if you hold one input only, if I held link 5 here, the rest of the mechanism would be floppy, right? So you need 2 inputs. I could get a friend here to hold link 2. I'd hold link 5, and that would fix the mechanism. So we need 2 inputs. Okay, so that means independent variables as inputs, we need 2 of them. So let's say we can only solve this if we have those 2 inputs. So I'm going to say, as my mechanism, I'm going to set theta 2 and theta 5 as inputs. Those are my independent variables, okay, equal to my mobility. And what's left? Left is going to be our unknowns, and we're also going to have some constants. Okay, and in the language of vector loop land, each of our R vectors has a, right, we wrote it out like this last time. It has a length, each vector has a length and an angle. So those are our potential variables, angles and lengths. For this mechanism with no sliders, all the lengths are constant. So we could say all of the R's are constant. Not true for anything that has a slider. Or some other times you'll have R's that are varying. But for this mechanism, they're all constant. So unknowns is basically everything else almost, right? So theta 3 and theta 4. Right, those are unknown. Those are angles that are varying over time and unknown. What about theta 1? Angle of R1. That's our boring vector just along the ground. It's constant, right? Theta 1 equals 0. That's a constant. So we're not going to count that as one of our unknowns. Anything else that we're missing? We have, there's 10 variables, right? 5 vectors, 10 variables, 5 R's and 5 thetas. They should all appear here. So there should be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we hit all of them into one of our 3 categories. Any questions about our variables? Yeah?
Why did we add link E?
Why didn't we add a link E? Like I didn't put any vectors out there. For now, I said we're not concerned about E. Like it's a point there, and you have to decide what to include in your loop. So if I did ask you to find velocity of E, we would need a different vector loop that goes out there somehow. Okay, but I said we're not doing that. So even though E exists, you don't have to go there on your loop. So this basic loop captures all of the link motions. So to form your loop, you need to know what are you solving for, right? If you're solving for something about E, then E needs to appear in your loop somehow. Your vectors need to come out here and touch E. I'm saying for now we're not studying point E, we're just studying the basic mechanism, so we just ignore that. We'll come back and look at other, we'll look at some links like this that, and how we're going to include them. For now, let's just erase that, and we're just doing the basic part of the mechanism. Okay, so this is our constants, independent variables, and dependent variables. I'm going to do another example here where a vector loop doesn't capture the motion of the mechanism. And we're going to look at gears. So we're going to see that this is a failed example. So we're going to have two gears. Okay, let's call these links 2 and 3. And we're going to have points A and B as their center pivot points. And their connection point, where there's no slip, would be here at point C. So I'll be really clear and write no slip there for gears. Okay, so what's the mobility of this mechanism? How many inputs would you need to give to specify both of these? There's 2 links, so probably it's not bigger than 2. So I would say it's either 1 or 2. How many, like if I held link 2, if I held this gear, the other gear wouldn't be able to rotate either, right? So that indicates to us that the mobility is 1. Mobility is 1. So we should be able to form a loop, or our goal would be to form a loop that has 1 independent variable and maybe two dependent variables. But how do we form a loop here, right? Unlike our turning pairs up here, this one, there's not a lot of points to look at, right? We have point A, B, and C. That's basically all. So we could try. I'm just going to draw them over here, just so it's a little less cluttered. Here's point C. And here's point B. You can draw it on your mechanism if you can do it uncluttered. So like, there's other points that you could go to, but those aren't describing the motion of the mechanism, right? A, B, and C, that's everything, right? So let's try and form a loop here. I could have my first vector, R1, going between the 2 base points. And then we have R2, this one's like it's attached to link 3, going back here to C. And another one here. So this is the loop R1 plus R3 plus R2, and we get back to the beginning. So this is like a candidate loop. And we'll ask ourselves, does this capture the motion of the mechanism? Right? Our loop up here for the 5 bar, if you move the mechanism, all the vectors move with those links. So it captures that as motions. For this one, though, imagine turning the input a little bit. So I turn the crank here, link 2, 10 degrees. But the contact point stays at the same location, right? Because they're rolling on each other. So the contact point stays here. So even as the links move, these vectors don't, right? So this is an example where this loop doesn't capture the motion. It doesn't, if these move, these vectors stay the same because the contact point C, it's always at this same location. C is always here. So this loop doesn't capture the motion. And in general, gears aren't going to make a lot of sense to use a vector loop method to study them. The good news is gears are actually a simple gear set like this. 2 gears on each other is really straightforward to study separately. Like, you can just have a gear ratio which we'll study later on, is the ratio of their two diameters. And that's their speed ratio. So we can study gears pretty straightforward without resorting to things like vector loops, or you could also use another method like velocity polygons. I gave you a problem that's kind of like two gears. Velocity polygons, you could study these. Vector loops, it doesn't really work. Questions about that one? So you're not guaranteed to have a vector loop that can solve every mechanism problem. Off the top of my head, I can't think of other examples that will always fail other than gears. Gears are kind of special in that regard, that the geometry of that contact point doesn't really change. But you might run into some, and you might have to resort to other methods to be able to study those. Okay. So let's go forward and assume that we're able to capture all of our motion. And we're going to do sort of a full problem now. And we're going to study a slider crank. So this is our first problem that has a slider in it. So we'll see how that appears. And we're going to go through and we're actually going to solve, instead of just writing out loop equation as a boring equation, we're going to actually solve for the unknowns. Okay, and we're going to study an offset slider crank. Offset, we've studied these a few times before. So my crank's going to be, or my slider's going to be down here. Okay, so this is our offset slider crank. And the amount of offset is the distance from this line of motion of that slider point perpendicular up to our pivot. Okay, so that's our offset. Okay, so the problem might be given the input theta 2. So that's our input theta 2. Let's find the output, which is location of the slider. Okay, I'm going to label my links so we can talk about these 2, 3, and 4. So let's find the x position of link 4. So I'll define that now. We can define it however we want, but I'll define it as how far right of the pivot are we. Okay, so that's my x4. How far right of the pivot are we? Good, so that's our problem. And ideally, our outcome will be theta 2 equals, in some big equation that has, x4 equals some big equation that has theta 2 in it, and a bunch of constants. Okay, so the link lengths are constant, but this slider is moving, so we'll just keep that in mind as we develop our loop. Okay, before we get into anything, let's think about our mobility, make sure we understand what's going on and what we're going to need in our loop equation. Mobility of a slider crank is what? We've studied it 10 times or more. It's 1. So one input can satisfy or can set the whole mechanism. And that makes this question answerable. If mobility doesn't equal 1, we wouldn't be able to answer that. But it does, so we're OK here. Good. Let's get into it. Let's design a loop. So we need a loop that captures theta 2 input. It needs to capture x4 as the output. And link 3 should be in there too, right? Because link 3 connects the two. So if there's not a vector along link 3, your loop isn't going to tell you about how this mechanism moves. So that's kind of what we need to design. You actually have some choices here. But my suggestion to you is, first think about your input and put a vector there. So we're going to do that. Let's put a vector on link 2. Right there. And I chose my vector pointing up. There's lots of questions. There's been questions about up or down. I chose it up so that theta 2 matches our definition. So that means our theta 2 is our input to the problem, is the same as our definition of theta 2 that we use all the time up at the top there. Okay, so that one's up. Next, let's think of our output. We want a vector that captures this horizontal sliding motion. So it may be tempting to draw a vector like from the origin down to that point, but that has an angle and a length. So a simpler vector that captures x4 motion would come from this point here. Right, that point is always there. It's right beneath here and right along that line. So if we put a vector here, and let's just point it right. You could point it left if you wanted. I'm going to call that R4. Its angle is constant. I'll list some constants here as we go. So the angle of 4 is constant, but its length is the same as what we want to calculate as our output. So converting x4 into vector loop language, that's the same as the length of link 4, R4. Okay, so that's going to lead to a really easy to interpret answer. If we can calculate R4, that's our answer directly. Okay, so those are the important things. The other piece is link 3. So logically, let's just put a vector right along link 3. You can point it up or down. I'm going to choose to put mine. I'm going to put mine up, so the theta 3 is defined right there. You could angle yours down and just have a negative sign. Okay, do we have a complete loop though? We've hit everything we need to, but no, our loop is not complete. So if we start writing our loop equation, I'll start at this base pivot and go around clockwise. We have R2 minus R3. We're going clockwise, so we also have minus R4. And we want to set this equal to 0, but we haven't completed the loop. So we have to add an additional vector here. I'll just call it R offset. You could call it R5 or whatever you want. And that's a constant. And that gets us back to the beginning. So we can set our loop equal to 0. So we can start tallying up our dependent variables, independent variables, and constants. Make sure we have enough. And have we developed a loop that we can solve? OK, so constants, we just said that offset thing, that's a constant. So we'll put all those in the constant list. And let's just go through the others. R2, its length is constant, right? Same for R3. Do we have any other constants? I think this is good. OK, dependent and independent variables. I always have to think twice to keep track of which is which. Independent means we can choose them. Those are our inputs. So this would be theta 2. It equals our number of mobility. There's one independent variable, so that's good. Dependent variables, those are our unknowns. Dependent variables. So the only things that remain should be dependent variables. That's going to be theta 3 and R4. Let's just do a little check here. We have how many vectors? 1, 2, 3, 4 vectors. So there should be 8 variables. 1, 2, 3, 4, 5, 6, 7, 8. Good. We've counted everything. We have 2 dependent variables, 2 unknowns. That means we can solve it. So those are our 2 checks. Number of dependent variables is 2. Number of independent variables equals our mobility. That means we've made a loop which we can solve mathematically. And if you come up with a loop which can't be solved, it doesn't mean it's an invalid loop. It just means once you go to the next step of trying to do the algebra and solve for your unknowns, you'll just never be able to solve for it. OK, any questions about our loop formation before we actually go into solving these? Yeah.
I understand that we need to have our mobility equal to the number of independent variables, but
Yeah.
why did we need the dependent variables equal to?
So each loop can solve for 2 variables.
Yeah.
Because we're going to have a horizontal components and a vertical components equation. 2 equations, solve for 2 unknowns. Yeah, and we're going to do that right now. We're going to do that now. So as any vector loop problem, your goal is going to be solve, once you formulated it like this, is solve for the dependent variables. Okay, and our dependent variables, theta 3 and R4. We have 2 of them. Ultimately, what we said was what we wanted at the end was this x motion. We didn't necessarily care about theta 3. So it may be possible to solve for R4 without even solving R3. Although we'll see in practice, usually you have to solve for all of your unknowns. All of your unknowns. Solve for dependent variables. Those 2. So let's just write out our loop equation. I wrote it here. We're going to rewrite that in full format. Full format. So what do we have? Keep track of our signs. R2. So by full format, I mean, let's write out each vector with its length r, lowercase, oh, oops. I doubled up on my r's. With its length r and its angle theta. Okay, minus R3. The good news is these always appear the same. Every vector is the same because we kind of standardized that last time. Now we're going to subtract R4. And adding our offset. That's our offset. Okay, and these equal 0. So writing like this is kind of a vector format, right? Horizontal and vertical components. And these are each an independent equation. So both of these equations should be satisfied all the time. And now we've gone from mechanism language and mechanism interpretation. We've sort of devolved that problem into just an algebra problem. So for now, we can forget about the mechanism. Let's just solve this as an algebra problem and use our trigonometry tricks to solve it. We'll use our constant list. So we have a bunch of things that are going to go to 0 or 1 or something like that. So let's write out what those are. Right? So, okay, theta 4 is a constant. Where's theta 4? Theta 4 equals 0. So what terms are going to go to 0 because of that? Cosine or sine? It should be, if you just look at R4, it has no vertical component, right? So that, of course, is the sine theta 4 equals 0. Good. Cosine theta 4 equals 1. So we just plug in everything we know from our constants. Okay, our offset is a constant. R2 and R3 are constants, but they don't disappear from our equations. So now we can write out, let's sort of simplify this. Let's just write out our horizontal component equation. So we have R2 cosine theta 2. And I'm writing cosine as C and sine as S just to make our equations a little more concise. R3 is not affected by our simplifications. But R4 is. So we have cosine goes to 1. So we have minus R4. Oh, we also have this offset, right? Theta offset equals what? Based on how I drew it there. Is it, it's vertical, pointing up. So that's 90 degrees, right? So what does that do to our cosine and sine? Sine goes to 1, yeah. Cosine goes to 0. Okay, so we can simplify this a little bit. This is our horizontal component, so our offset doesn't appear at all. So there we go. Our horizontal component equation just has 3 terms, equals 0. And we'll call this equation 1. And we'll do the same for our vertical equation. R4 doesn't appear, right? Sine of theta 4 went to 0. We just have our offset now. And we get our our vertical equation. Also has 3 components set equal to 0. So we have 2, you'd call these simultaneous equations. And we're going to solve them for our unknowns. X4, which here we're calling R4, and theta 3. So you can use whatever tricks you want. Luckily for these mechanism problems, these solutions, this turns out to be just about the easiest one you can do. But the good news is that there's a couple of algebraic tricks which you can solve basically every one of these problems using. In next lecture, we'll go over a more complex problem. For this one, basically let's decide which equation to look for first, which one to try and solve first. Ideally, you could just solve for one of your unknowns using one equation. So R4 appears in the first equation. But the problem with solving for R4 is that theta 3 is also here, right? So the first equation, we could solve it, but theta 3 we don't know. So this has 2 unknowns in it. The second equation, equation 2, only has 1 unknown. So that's lucky. Usually you'll have 2 unknowns in each equation. This one only has 1 unknown. So we can solve equation 2 by itself, and then we can plug that into equation 1. So let's do that. Let's use equation 2. And this is my way of explaining what I'm doing and writing it. I encourage you to also explain your solution method to me when you're solving problems. If you number your equations and then say which one you're using, because you're going to be very tempted to skip some steps. Probably already you've said writing this out first and then doing this is a waste of time. If you're skipping steps, you need to really be clear about what you're doing. Okay, so from 2, we can just solve for theta 3. So I'm going to do an intermediate step. I'm going to solve for R3 sine theta 3. That way we can keep our pluses and minuses correct. Okay, so I'm moving that to the right-hand side, basically. R2 sine theta 2. And we'll get plus R offset. Does that look good? Yeah. Okay, so we'll divide by R3 and do inverse sine. Okay, and we're done. We're done with our problem. For theta 3, that is. For theta 3. So we could plug this in to MATLAB, put in theta 2. That's the only unknown here, right? All these other things are constants. You could know those values. And you can calculate theta 3 and plot it out. So the next step is going to be solving equation 1 for our remaining unknown. Okay, so we want to solve for what? R3. So let's solve for R3 cosine theta 3. No, we want to solve for R4. That's a little easier. Okay, R4 equals negative R2 cosine minus R3 cosine. Okay, so this one's, it's really simple. We just plug in theta 3. Did I make a mistake here? Should this be plus? Yeah. And this one's minus. Yeah, thanks. Okay, so just plug in your R3 or your theta 3. I'll call that equation 3 here. Plug that in there, and you can write out your full solution. I'm not going to write it out because my space is out here. But that's just an algebraic expression for our output of the mechanism. That's what we wanted. X4 is the same thing as R4. So we've captured the output of the motion, and once we've solved it, we directly get the answer. Any other questions about this one? So what if I wanted to solve for velocity? The good thing about this method is that once we've set up our loops, and once we've done our checks that our loops are solvable, and that we have the right number of dependent and independent variables, if we want to find velocity, we don't need to go back to our mechanism again. We just have an algebraic problem, and we're going to take time derivatives. So R4 dot, if we take the time derivative of this equation, keeping in mind what's constant and what's varying, that's going to be the same as the velocity of our output. If we want to take acceleration, we just do the second derivative, R double dot. And that's the real power of this method, is we put all of the difficulty of solving these problems into basically doing a bunch of time derivatives, which sometimes can get gnarly if we have complicated equations. This one is pretty simple, although you have cosine of inverse sine. You might be able to simplify that, but that might be a hard time derivative to do. But the other ones we'll see are not going to be that bad. So this is all for today. Next time we'll get into a more complex mechanism, and we'll get into taking time derivatives and see what those look like. Thanks, everyone.